So my favorite website for this is Oklahoma State. Put out a really nice description of this. If you like Google like molecular geometry Oklahoma State, you should be able to get an exact copy of it. But there's a variety of reasons why I like this. First off, if you click those blue links on the right, they show you 3D rotational diagrams of what they look like. I think it's really valuable, especially for tetrahedral, because it's kind of hard to understand what that actually looks like in 3D, because everyone gets that confused with square planar. So we're just going to move down this chart, and then we'll draw pictures to look at things. Okay. So if I have two bonding atoms and no lone pairs on my central atom, I have a linear structure. Nice and easy. Bond angle is 180. We can't do anything else. Like we can't have a 1 and 1. For our bare basics here, we're going to stick with the linear. Now, if I have three bonding groups, meaning I have 3 sigma bonds coming off that, right? Or I could have 3 sigma bonds and a pi bond. We're just looking at actual bonds here. Single bond, yeah, single or double. So this is why in our sp2 hybridized orbitals, we have trigonoplanar shape. Even though it has 4 bonds, it's 3 sigma bonds that we're looking at. So if I have 3 sigma bonds and no lone pairs, I get a trigonoplanar shape, which if we look at it, looks like this, which is they're all in the same shape with each other. Now, what's important to realize is we can also draw this a little bit more 2D flat, is we could say we have our central atom, then we have 3 things out here. This makes up a circle, right? Mm-hmm. So this is all 120 degrees each for the bond angle. Easy to remember. Now my question is, this is for 3 bonding, 1 or no unbonding. If I were to do 2 bonding, 1 unbonding, my electron geometry is going to still be trigonoplanar. Okay? But my molecular geometry changes. It becomes essentially like it's the more specific version of what's going on, because it takes into account not just total electrons, but bonding and unbonding. So this molecular geometry, how we can draw this, and how I like to think of it, is you just take away an electron and put a big, ugly lone pair in its place. So I'm just going to take away one of these bonding electrons and put a lone pair there. Lone pairs, they're lonely, they're big, ugly, and repulsive. So they take up a lot of space, and they push these molecules away. So what happens here, what do you think happens to this angle? Does it get bigger or smaller? Smaller. So this bond angle will be less than 120 degrees. Okay? And this is now, the molecular geometry is called bent. So I want you to remember that this bond angle is going to be a little less than 120 degrees, because bent happens in trigonoplanar structures and in tetrahedral structures. And the difference between them, even though it's the same molecular geometry, their bond angles change because of these big ugly lone pairs. Okay. So next, we're going to look at tetrahedral. So classically, tetrahedral is the four constituents spread evenly apart, and because they're spread evenly in space, each of these angles between any 2 groupings is 109.5. Okay, and the way we draw this on paper, and you may see this a lot, we'll have our central atom, then we have one sticking straight out, one sticking this way, then we have one that's more bold, and you just have to imagine it's like pointing directly at you, and then one that's dashed pointing into the paper. And what's important to remember here is this bold line and dash line have to be next to each other, just colloquially for it to make sense. So, you know, some people they would try and draw a dash line over here. No, because this gets in the way. So each of these angles are 109.5. So now we're going to play a game, and this is for 4 bonding, 0 unbonding. Its electron geometry is equal to the molecular geometry when you have no unbonding. And in this case, that is tetrahedral. Okay. Now, I'm going to take away an electron because I want to see what 3 bonding, 1 unbonding is. What is the electron geometry for this? Tetra. Yep, tetrahedral, doesn't change. So now I care about the molecular geometry. And without cheating, because we want to be able to, like, you have to kind of know the names, but at the end of the day, we can figure out what it is. So let's just say I get rid of this top electron here. Now I have my lone pair here that's big, ugly, and repulsive. What's going to happen to each of these bond angles? Yep, so it's going to be less than 109.5, maybe let's just say it's 108.
And that's trigonal.
Yes, awesome. It's trigonal pyramidal because we have 3 bases here, and it makes a pyramid. So the structure looks as it sounds. Now let's go ahead and figure out, let's go 2 bonding, 2 unbonding, or 2 lone pairs. So I'm just going to get rid of this one here. You can pick anyone to get rid of. Put our lone pair in. Boom, big, ugly, and repulsive. What do you think this bond angle is?
Less than 109.
Yep, and less than even 108 before, so maybe it's like 107 or 106, right? You don't necessarily need to know the specifics of what it is. You just got to know it's less than 109. And what is this shape then?
Maybe seesaw.
It's not seesaw. We'll get to seesaw later. Nope. You're getting ahead of yourself. We've seen this shape before, right? This looks just like this.
Oh, is it just bent?
This is the bent.
Oh.
So, but notice that even though it's the same molecular geometry as the trigonoplanar bent, it has a different bond angle. The trigonoplanar bent was maybe like 119. This one's more like 107, 106. Okay? And it's because we have 2 big, ugly lone pairs hanging out here, and it's causing even more repulsion. Plus, these angles are smaller inherently because of the original tetrahedral shape.
Okay.
So that's tetrahedral. Now we're going to get into your seesaw and stuff. So if we're going to look at the trigonal bipyramidal. So trigonal bipyramidal is named, I don't like this drawing, but I like to say like, okay, here's my central. And then we have 2 components that are on the axis. And then we have 3 components around the equator. Okay, so from this, from an axial to an equator, my bond angle is 90 degrees. From axial to axial, what do you think my bond angle is?
180.
Yep, 180. And then between equatorial, what do you think my bond angle is? What does it look like in the middle here?
A circle.
Yeah, so circle divided by 3?
So 360 divided by 3.
Yep.
120.
Yep, same thing as trigonal planar. So it's kind of like we have a trigonal planar mixed with a linear compound together, okay? The other way to look at it is why it got the name. Do you understand why it's called trigonal bipyramidal, or you just think they're just throwing random words at you?
Is it because there's 5 instead of...
So the trigonal component means that there's this 3 part here, and bipyramidal means there's 2 pyramids. So if I were to draw lines from here, here, and here, and down here, here, and here, it kind of have 2 pyramids like back to back. So that's how they gave it its name. They don't necessarily explain that in class. It's kind of like, it's kind of frustrating because you're like, why is it called that?
It's just a name.
Yeah. So that helps you. Now you remember, okay, if I have 5 constituents, it's trigonal bipyramidal for the electron geometry, right? And in this case, when we have this, that's the molecular geometry as well. But now you understand like what it looks like. So even if you forget, the structure, it kind of gives you a better idea. So now what happens if I have 4 bonding, 1 unbonding? So I get rid of one of these. Let's say I get rid of, so here's the thing. When you do this rule of getting rid of things that I keep talking about, we always remove, for trigonal bipyramidal electron geometry, remove from the equator first. Okay? So that means I'm going to remove one of these 3 first. I don't touch the axial ones.
Okay.
Okay? So I'm going to remove just this one. So what shape does this kind of look like now? I got 2 legs and a long board.
So that looks like seesaw.
Yep. So this is where the molecular geometry is seesaw. Okay, let's go for 3 bonding, 2 non-bonding, 2 lone pairs. And let's say I get rid of this one right here. What does this look like? Remember, this is pointing out at you. This angle is going to be 180 degrees still. Remember, axial doesn't change. So it can't be trigonal planar because trigonal planar would have 120 degrees. We know from here to here is 90 degrees. So what happens if I have a 180 degree angle and a 90 degree angle? Which letter of the alphabet?
T. Oh,
this is T-shaped. Okay. So don't forget your angles there because yes, you could argue, oh, it's trigonal planar, but because of the way the lone pairs are situated, they are maintaining this T-shaped. Their repulsions don't allow it to be evenly divided. All right, and last step, let's say I have 2 bonding, 3 non-bonding. What does my shape look like?
Is it just linear?
Yep, linear.
Oh, nice.
So how this actively works, and for example, like when you would use this is, let's go to the T-shaped orbital here. Let's see if that's any better. So for BRF3, cool. So notice that we have 2 non-bonding pairs and 3 bonding. And then if we were to draw this out, we could say, okay, BR has a an F and an F, and it has 2 lone pairs, so we'll just put the lone pairs here and here. Remember, because the lone pairs have to be on an equator for trigonal planar electron geometry, that's why we put them here and not at the poles. Okay, and then here we have the F. So that's how we get our T-shaped structure. So lone pairs have to be at the equator, because that's what's removed first in the trigonal bipyramidal electron geometry. So, is that all making sense there?
Mm-hmm.
Okay, so then our last one to really work through is octahedral. So octahedral occurs when we have a central atom, and we draw straight up, and we draw straight down. We have 2 axial components, and then we have 4 equatorial components. Okay, so the key for octahedral is when we remove axial first. So we're going to remove these 2. So when I go for 5 bonding, 1 non-bonding, I'm going to eliminate one of the axials. You can pick or choose. Let's just get rid of the bottom one. Notice what I have here is I have a square base that connects up to form a pyramid. So this shape is square base makes a pyramid.
Square pyramidal.
Yep, exactly. Square pyramidal.
Where does it make a pyramid at the top?
So think of like these reaching up to the top here. So it kind of looks like a pyramid. It's a little tough in 3D. You can actually maybe see it a little bit better here with here's my axial components and they reach up to here. Okay, so now let's say I want to do 4 bonding, 2 non-bonding. Where am I going to remove my next one from?
The top.
Yep. So what is this shape?
Square planar.
Square planar. What's the angles between each of these? 360 divided by 4. Circle in 4 equal parts.
Would it just be 90?
Yep. And notice when we had the axial components, axial to equatorial is 90, equatorial to equatorial is 90, but axial to axial would still be 180.
So this to that is 90 and this to this is 90?
Yep.
Okay.
90, 90, yep. All right. Let's say I go 3 bonding. Actually, I don't think we go this far. I'm getting a little too ambitious there. I'm sure it's a thing, but I think it's outside the scope of our class. Yep, so there's square pyramidal and square planar. And here's a picture of square pyramidal again, so you can see it's a little bit more, that's where the pyramid comes in.
That makes way more sense.
Okay, so you make sense that, and octahedral, we didn't really look at it, but what it means is there's 8 faces here, because I got my 4 faces on my top pyramid and my 4 faces on my bottom. Cool.
I have a